Hi, I just wanted to do a very quick video on this type of question which comes up at A level because what's quite interesting is when I'm actually teaching this, it looks very, very similar to what students have actually been able to do very well at GCSE, and I just think it's quite surprising that given the links between the GCSE chemistry areas on enthalpy and A level, that there are a little bit of difficulties that students still have. So just feel free to pause the video and to have a quick look through the question. But essentially the question is actually about this side over here. The equation for the combustion of octane is shown, so that's quite nice. It actually shows all of the bonds in octane. I've actually highlighted this and I will talk through as to why it is in a moment. But the question actually shows the entire molecule, and then it says 12.5 times oxygen. It's got the oxygen double bond. Then it gives you 8 carbon dioxide molecules. This is CO2, and the carbon dioxide molecule is drawn quite clearly. And then you also have 9 water molecules. So the questions usually are designed in such a way that they will actually give you the mean bond enthalpies in kilojoules per mole. So if you're a student and you're having difficulty with this, one of the things that I've actually suggested to my students as well is, and don't think of it as being kind of like, oh, this is a really basic way of looking at this. We should be really working in a more advanced way and a quicker way. But breaking it down into something like this will actually really help. So I would suggest while you're going through it, use a highlighter. So you can identify that the CC bonds are in your reactant here, which is the octane. So you've got 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, 1, 2, 3, 4, 5, 6, 7. So you've got 7 bonds from 8 carbons. So those need to be snapped. So the mean bond enthalpy, which is a positive value, it's essentially the amount that you have to supply in kilojoules to break up 1 mole of those particular bonds. So if you've got 7 of them, you will have to do a multiplication by 7. So what you can do is, when you're actually doing this type of question, what I suggest you do is put an R just underneath the table, and that would represent reactants, and then a P to represent products, and then try and figure out how many of each of these bonds you have to break. So I've done that for the CC bonds. I've figured out already for the video that you have 18 of the bonds, the CH bonds, which I've highlighted in blue. Now, you actually have this 12.5 over here, and some students think, well, how can you have half the bond? But essentially what you're doing is you're actually working in terms of moles. So this 12.5 actually represents 12.5 moles of these molecules. So it does actually make sense, because for every 1 mole of this molecule, you will need to react it with 12.5 moles of O2. So 12.5 multiplied by 498 is the figure that you want for this part of the equation. So that gives you the total enthalpy, that enthalpy change that you need to supply in order to break each and every single one of these. So don't be afraid to work with halves, okay? If you don't want to work with halves, you'll have to multiply it all the way through, but all of your numbers will be doubled. So, just a quick thought on that would be, well, you could put a 2 there, you could put 25 there. This would have to be a 16, and that would be an 18. And it all does work out to give you the right answer, but you don't have to double it through. So that deals with the reactants. Now, what you can do is you can put a little P for product, and then tot up the number of each of these bonds that are breaking down. So you've got an 8 here. You've got to remember that there are 2 C double bond O bonds in carbon dioxide. So initially what you'd have to do is you'd have to multiply that by 2 and then multiply it by 8, so you get 16. Do the same with 9 times 2 equals 18, and you're almost ready to go. So calculate reactants and products, subtract is a good way of remembering how to take your figures forward. So if you calculate the total mean bond enthalpies in your reactants, it's 7 times 347, and then add that to 18 times 413, and also add that to 12.5 times 498. Now that actually gives you 16,088 kilojoules per mole for this particular question. Now do exactly the same for the products. You've got 18, because it was 9 times 2 of these, times 464. So 18 times 464, and then add that to 8 times 2 times 805. So that should give you 21232. Now it's worth pausing the video and just making sure that your calculation is correct. Sometimes people put an extra brackets here or there and they miss that out. So just make sure that you're okay. So that's the first 2 stages. Then the last 2 stages, you're almost there. Remember, it's reactant and product subtract. So with these values, you have to get the total number of kilojoules per mole from the reactants, and from that value, take away the total number of kilojoules per mole in the product. So 16,088 take away 21,232, and that gives you a figure of minus 5144, which does make sense because this signifies an exothermic change and combustion is exothermic. So it's a typical component of petrol. So you can actually just do a quick like thought there to make sure that it does make sense. And that basically is how you do that. So what I wanted to do is I just wanted to come up with a very quick and easy method for you to refer back to if you're ever stuck. Do like and subscribe. I appreciate all the support for the channel, and good luck in your A-levels. Bye.